What if I told you the moon's far side is fundamentally different from what we see every night? Like uncovering a secret side of a familiar face, China's Chang'e E6 mission just returned with the first ever samples from the lunar far side, revolutionizing our understanding of Earth's only natural satellite. Initial analysis reveals striking differences between the two lunar faces, a discovery that could explain why they evolved so differently over billions of years. The far side contains significantly less water than the near side, pointing to a mysterious lunar history we're only beginning to unravel. These findings represent a critical turning point in lunar science in our quest to understand cosmic evolution. The lunar divide, two faces of the moon. The moon isn't the uniform sphere many assume it to be. In reality, our celestial neighbor has two dramatically different faces that evolved separately over billions of years. This asymmetry has puzzled scientists since we first glimpsed the far side in 1959, when the Soviet Luna 3 spacecraft captured the first images of this hidden lunar landscape. When you look up at the moon from Earth, you're always seeing the same face, what astronomers call the near side, with its distinctive dark patches visible to the naked eye. These areas, called Maria, Latin for seas, formed when ancient volcanic eruptions flooded large impact basins with dark basaltic lava between 3 and 3.5 billion years ago. The near side's geography features these Maria covering about 31% of its surface, including the Sea of Tranquility, Apollo 11's landing site, the Sea of Serenity, and the Ocean of Storms. The far side, however, appears to belong to an entirely different world, like two halves of an ancient coin with entirely different engravings. The dark Maria that characterize the near side are virtually absent, covering less than 1% of the surface. Instead, the landscape is dominated by craters upon craters, a rugged, heavily pockmarked terrain that bears little resemblance to the moon familiar from Earth. Why would two sides of the same celestial body develop so differently? The moon's tidal locking explains why we always see the same face, but not why the hemispheres evolved along such different geological paths. Scientists have proposed various explanations. Perhaps the moon's crust is thicker on the far side, impeding magma flow. Maybe Earth's gravitational influence affected volcanic activity, or possibly a large impact distributed heat producing elements unevenly, causing more volcanic activity on the near side. These remained theories because since Lunar's first grainy images, we lacked the most essential evidence, actual rock samples from the far side. While the near side has been extensively sampled, with over 380 kilograms of material returned by Apollo and Luna missions between 1969 and 1976, no mission had ever brought back a single gram from the far side. The South Pole-Aitken Basin on the far side represents a geological treasure trove. This immense impact crater spans 2,500 kilometers in diameter and reaches depths of 8.2 kilometers, making it one of the largest known impact structures in our solar system. Formed approximately 4.3 billion years ago, its tremendous depth likely penetrated deep into the moon's crust, possibly excavating material from the lunar mantle and creating a window into the moon's interior composition. The basin contains evidence of volcanic activity different from near-side Maria, with deposits showing distinct chemical signatures. It preserves records from the late heavy bombardment period, approximately 4.1 to 3.8 billion years ago, when the inner solar system experienced intense asteroid impacts. The region may also contain clues about the moon's magnetic history. As studies suggest, the moon once had a global magnetic field that disappeared around 3.2 billion years ago. Given these potential discoveries, the South Pole-Aitken Basin became a priority target for China's lunar exploration program. The Chang'e 4 mission made history in 2019 by achieving the first ever soft landing on the far side within the Von Karman crater inside the basin. While this mission analyzed surface composition in situ, it couldn't return samples to Earth for detailed analysis. Chang'e 6 transformed lunar science by successfully landing in the Apollo Basin on the far side on June 1st, 2023, and returning approximately 2 kilograms of lunar material. These precious samples provided scientists with the first ever physical materials from this mysterious hemisphere, allowing precise analysis of mineral composition, water content, isotopic ratios, and age. Initial findings have already begun reshaping our understanding of lunar asymmetry. The samples contain evidence that volcanic activity on the far side continued for at least 1.4 billion years, longer than previously thought. They also reveal significantly less water than comparable near-side samples. Most importantly, they offer direct evidence explaining the moon's asymmetrical development. Compositional differences between near-side and far-side materials point to fundamental variations in formation conditions and evolution. The success of Chang'e 6 highlights how limited our previous lunar exploration had been. Despite Apollo's monumental achievements, half the moon remained completely unexplored by sample return missions until now. The technological challenges of operating on the far side, particularly the communication barrier created by the moon blocking direct radio signals to Earth, prevented earlier missions from accessing this territory. The Chang'e 6 samples connect directly back to those first Luna 3 images that revealed the moon's hidden face. What began as grainy photographs showing an unexpectedly different lunar hemisphere has evolved into physical samples we can analyze in Earth laboratories, bridging a 64-year gap in our exploration efforts. As we examine these groundbreaking samples, we're gaining insights into fundamental processes that shaped the entire inner solar system. The lunar far side preserves a record of the early solar system relatively untouched by volcanic resurfacing. By comparing both hemispheres, scientists can construct a more complete picture of our solar system's formation. With these new samples in hand, we enter a new era of lunar science. But collecting them required overcoming tremendous technological hurdles that previous missions couldn't surmount. Let's look back at how lunar exploration began and the limitations that kept us restricted to the moon's near side for so long. Apollo's legacy, the first giant leap. July 20th, 1969. The world watched as Neil Armstrong took those first historic steps onto the lunar surface, declaring it one giant leap for mankind. This moment marked the pinnacle of human space exploration, the culmination of a decade-long race that pushed technology to its limits and expanded our understanding of both Earth and its celestial neighbor. Over the next 3 years, 5 more Apollo missions would land on the moon, with 12 astronauts exploring the lunar landscape and returning with a scientific treasure trove of moon rocks and soil samples. Yet for all their remarkable achievements, the Apollo missions had significant limitations. These pioneering expeditions explored only a tiny fraction of the moon's surface, all on the familiar near side that faces Earth. The far side remained completely untouched by human hands or sample return missions, a situation that would persist for over 5 decades until Chang'e 6's breakthrough. The Apollo program represented an extraordinary technological achievement for its time. The missions utilized advanced rockets, spacecraft, and computers available in the 1960s and early 1970s. However, these technologies were primitive by today's standards, with computational limitations that restricted the spacecraft's autonomous capabilities and required constant human monitoring and control. More importantly, the Apollo missions operated under a fundamental constraint: the need for continuous direct communication with Earth. The spacecraft and lunar modules were designed around a direct line-of-sight radio link between the astronauts and mission control in Houston. This communication architecture worked perfectly for near-side operations, where radio signals could travel unimpeded between Earth and the Moon. However, it made far-side exploration effectively impossible. The Moon itself blocks all direct radio signals from the far side to Earth. Without relay satellites positioned in lunar orbit or at Lagrange points, astronauts landing on the far side would be completely cut off from communication with mission control during the most critical phases of their mission. In the event of an emergency, they would have no way to call for assistance or receive guidance. Given the already considerable risks involved in lunar landings, NASA deemed this communication blackout an unacceptable safety hazard. The Apollo program lacked the satellite infrastructure necessary to enable far-side communications. While technically possible to deploy communication satellites in lunar orbit, this would have required additional launches and spacecraft development at a time when the program was already pushing the boundaries of available technology and budget. Sample collection methods employed during Apollo missions were remarkably straightforward. Astronauts used basic hand tools including hammers, tongs, scoops, rakes, and core tubes to collect lunar material. They would visually identify interesting rocks, sometimes based on radio guidance from geologists on Earth, then physically pick them up and place them in sample bags. This approach was limited by what the astronauts could see and reach during their relatively short surface operations. Apollo core samples reached only 3 meters below the lunar surface at their deepest. While valuable, these samples only scratched the surface of the moon's geological history. Deeper material, potentially containing evidence of the moon's early formation period, remained inaccessible with the tools and time constraints facing Apollo astronauts. The geographical diversity of Apollo samples was similarly constrained. All 6 landing sites were situated on the near side, between 26 degrees north and 9 degrees south latitude, mostly in equatorial regions. These sites were selected primarily for safety considerations rather than maximum scientific return. Though later missions ventured into more challenging terrain with greater scientific interest, the entire far side and polar regions remained unexplored. Mission planning for Apollo required extensive human involvement at every stage. Landing sites were selected years in advance based on photographic surveys from lunar orbiters. The missions followed meticulously planned timelines with limited flexibility to adapt to discoveries or changing conditions. This rigid structure was necessary given the communication and computational limitations of the era, but restricted the mission's ability to respond to unexpected findings. Between 1969 and 1972, the 6 landed missions collected 382 kilograms of lunar material comprising more than 2,200 separate samples. Analysis of these samples revolutionized our understanding of the moon's composition, age, and formation history. They provided evidence that the moon formed approximately 4.5 billion years ago, likely resulting from a massive collision between Earth and a Mars-sized planetary body. Dating of the samples showed that major volcanic activity on the lunar near side occurred between 3.1 and 3.8 billion years ago, creating the dark Maria visible from Earth. The scientific value of these samples continues today. Scientists analyze Apollo samples using increasingly sophisticated techniques not available when they were first collected. Each new generation of analytical instruments reveals new insights from these 5-decade-old samples. However, all this knowledge came exclusively from the moon's near side, leaving half the lunar surface unexplored. Apollo missions never ventured to the South Pole-Aitken Basin or any other far-side location. This one-sided view of lunar geology left major questions unanswered about the moon's asymmetrical development and overall geological history. The same communication limitations constrained subsequent missions. The Soviet Luna missions, which returned small automated samples between 1970 and 1976, also limited their operations to near-side sites. After Luna 24 in 1976, no mission would return lunar material to Earth for 44 years until China's Chang'e 5 mission in 2020, also from a near-side location. Decades of technological advancement were needed to overcome these challenges. The development of powerful computers, autonomous navigation systems, artificial intelligence, and advanced communication networks eventually created the possibility of operating complex missions beyond direct Earth contact. These technologies, combined with China's systematic approach to lunar exploration, finally enabled humanity to access the moon's hidden face and return samples for analysis on Earth. The limitations of Apollo faced word failures of imagination, but practical constraints of 1960s technology. Now, over 5 decades later, new technology has finally overcome these limitations, unlocking the secrets of the lunar far side that remained beyond Apollo's reach. The Far Side Challenge, breaking new ground. For decades, the lunar far side has been tantalizingly out of reach for sample return missions. Unlike the familiar near side, which always faces Earth, the far side has remained largely unexplored for one fundamental reason. It's impossible to maintain direct radio communication with spacecraft operating there. The moon itself, a 3,474 kilometer diameter rocky sphere, blocks all direct signals between Earth and the far side surface. This communication barrier presented a seemingly insurmountable obstacle to exploration efforts. The moon acts as a natural fortress, with its far side holding geological secrets behind an impenetrable radio shield. A lunar sample return mission requires constant monitoring and control during critical phases like landing, sample collection, and descent. Engineers need to track the spacecraft's position, monitor system health, and transmit commands to adjust operations when necessary. Without this communication link, a spacecraft would be effectively flying blind during the most dangerous parts of its mission, even with automated systems. Sample return missions involve multiple precise maneuvers, landing safely, collecting and securing samples, launching back into lunar orbit, rendezvousing with an orbiting module, transferring the samples, and returning to Earth. Each step presents opportunities for failure, and even minor errors can cascade into mission-ending problems. For missions representing years of development and hundreds of millions of dollars, this communication void created unacceptable risk levels. China's solution to this decades-old problem arrived in the form of Keiqiao-2, meaning Magpie Bridge 2 in Chinese mythology. This 1.2-ton communications satellite launched in March 2023 specifically to support the Chang'e 6 mission. Its predecessors supported the Chang'e 4 mission in 2019, which achieved the first ever soft landing on the lunar far side, but didn't return samples. Keiqiao-2 operates from a remarkable location known as the Earth-Moon Lagrange Point 2, or EML2. Lagrange points are special positions where the gravitational forces of two large bodies and the centrifugal force of their rotation create equilibrium points. EML2 sits approximately 65,000 kilometers beyond the moon, directly opposite from Earth. From this position, Keiqiao-2 maintains simultaneous line of sight with both Earth ground stations and the lunar far side. The satellite functions as a cosmic relay station. Chang'e 6 transmits data to Keiqiao-2, which forwards it to Earth receivers. Similarly, mission controllers send commands to Keiqiao-2, which relays them to Chang'e 6. This communication bridge solves the fundamental problem that prevented previous missions from exploring the far side. Maintaining a satellite at ML2 requires precise navigation and regular adjustments. The satellite must perform station-keeping maneuvers to maintain its position against solar radiation pressure, gravitational perturbations, and other forces that could displace it. Equipped with advanced S-band and X-band communication systems, Keiqiao-2 enables high-bandwidth data transmission for operational commands, scientific data, and images. The satellite's large deployable antennas ensure strong signal strength despite vast distances, providing essential communication capability for Chang'e 6's complex operations. Even with the relay satellite, landing presented extraordinary challenges. The South Pole-Aitken Basin features some of the moon's most rugged terrain, heavily cratered with destabilizing slopes and potentially damaging boulders. Unlike the relatively flat mirror regions where Apollo missions landed, this terrain offers few large, level landing areas. Chang'e 6 navigated this uncertain terrain using onboard sensors and autonomous navigation systems. The spacecraft's descent camera captured images of the approaching surface, while radar altimeters measured precise distance. Onboard computers processed this information in real time to identify hazards and adjust the landing trajectory. The landing sequence required incredible precision. After entering lunar orbit, Chang'e 6 separated its lander from the orbiter. The lander performed a powered descent, adjusting its trajectory to avoid obstacles. In the final approach, the main engine throttled down as landing legs deployed. The spacecraft needed to touch down gently enough to avoid damage, but firmly enough to prevent tipping on the uneven surface. This landing sequence occurred with minimal Earth input due to communication delays. Signals take over 3 seconds for the 500,000 plus kilometer round trip between Earth, Yao-2, and Chang'e 6, an eternity during landing. Chang'e 6 relied heavily on autonomous systems programmed to make critical decisions without waiting for Earth-based controllers. Sample collection also required sophisticated automation. The lander analyzed surrounding terrain, selected suitable sampling locations, deployed collection mechanisms, and secured samples with limited human supervision. Operations robust enough to succeed even during communication interruptions. The lunar far side presents extreme temperature challenges. Without an atmosphere, surface temperatures reach 127 degrees Celsius during the 2-week lunar day and plummet to minus 173 degrees Celsius during the equally long lunar night. Chang'e 6 includes multi-layer insulation, radiators, radioisotope heater units, and materials with matched thermal expansion coefficient to maintain functioning systems across this dramatic temperature range. The successful mission represents a monumental achievement that effectively doubles the accessible lunar surface for future exploration. By solving the communication barrier that kept previous missions confined to the near side, China has opened an entirely new frontier. Future missions can now target any location on the moon, including scientifically valuable regions on the far side. Scientists can now study the entire moon, not just the Earth-facing hemisphere. The far side preserves a record of the early solar system, relatively unchanged by the volcanic activity that resurfaced much of the near side. It likely contains materials and geological features providing new insights into lunar formation and evolution, enhancing our understanding of the entire solar system's early history. With the communication barrier overcome, attention now turns to the advanced technology that enabled them.